Okay, here's a short video to talk about some of concepts of Unit 2.11 for Physics 167. So first thing is the analog versus digital signals. Analog signals are continuously varying signals. Our speech and in music from instruments, all the sounds we hear, okay, as well as records, vinyls, and magnetic. Yeah. Okay. So analog signals vary continually. Okay, whereas digital signals are broken into discrete chunks. Okay, so an analog signal would be like going up, just walking up a slope. Okay, whereas a digital signal is more like there are stairs with values in between that are not allowed. There are digital signals that are stored on a computer. As strings of zeros and ones, which are binary numbers. The advantages to, there are many advantages to storing and transmitting signals as digital, which are listed on the handout. Okay. But there are two things you get to choose when you're trying to set this up. So in practice, you'll have some analog wave coming in, and it will come into your analog to digital converter. Okay. And then that will be send out a binary number that will be stored computer file. And then when you want to listen to that, for example, in that stored file, we'll go into a digital to analog converter. That then will produce the sound wave again. Now, there are two choices that get to be made. They get to go into here. One choice is the sampling frequency. That will also be called the sampling rate. And the other choice is the bit resolution, also known as the number of bits per sample. So those are two choices that get to be made. And then those same numbers get also used when you're reconverting it back over here. So those are that's how it knows how to break up the wave into these discrete steps, and then how to go back to the continuous wave. Okay. All right. So here's an example of what that looks like. So this is the time axis. This is the amplitude axis. And we have some wave. Actually, that one will be too complicated to do. We'll just do a sine wave. Okay. The sampling frequency is what decides how often in time you're actually going to save the amplitude of that wave. Okay. So if I chose this sampling frequency, okay, where this time between these, this time between samples is the inverse of the sampling frequency. Okay, so higher sampling frequency, that would get closer together. But once I choose the sampling frequency, then that is like saying these points, the value of the amplitude of the wave at these instants in time are what is going to be saved by the analog to digital converter. Okay. So that's the sampling frequency determines the spacing of those purple lines and how many dots will be saved. The bit resolution determines how many possible values I can assign to those. So it's like cutting it this way, basically making a graph paper here. And these number of bits per sample basically means that anything below this line, so I will do an example with 4-bit numbers, binary numbers, okay? So anything that was below this last line would have a value of 0, 0, 0, 0. In between would have 0, 0, 0, 1. And between those two would have so forth. And then you just keep counting in this binary way of counting, which is a little different than what maybe we're used to. Definitely. And so forth. There are a few more about that. Okay, there would be, for a 4-bit number, there would be 2 to the 4th, or 16 possible amplitude levels. Or numbers that can be discretized, okay? So that means, based on my picture here, this first dot would get encoded as a 1000, 100 rather. This one would be coded as 110. This one turned out to be right on the line, but we'll just call it 0010. This one would be 0100. And then this one would be, these might both be 1000 or 1000. Okay, and so those little red numbers, those 4-digit numbers, those would be strung together, and that is what would be contained in the digitized sound file. Okay, so again, the bit resolution determines, as it says on your handout, impacts the amplitude resolution. So how many steps are there to go from the bottom to the top, right? So it's kind of like, okay, you're at the bottom, then you do a step, 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 etc., all the way up. Okay. Now, if I instead had like an 8, so that would be my 4-bit staircase. But then my 8-bit staircase would have 2 to the 8th, or 256 possible amplitudes. So essentially 16 for each of these. So that would be like going choo, 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 choo. I'm not going to make it 16. It makes it much finer stair step of possible amplitudes that you can assign. Okay, that's what it would be like for the 8-bit signal. Okay, so that's what we mean by the sampling frequency, the purple lines that determine when the dots will be saved, and then the bit resolution that will determine the actual binary numbers that are assigned to those values. Okay. So moving on to number 3 now. Roman numeral number 3 I'm talking about the bit rate. So the bit rate is also called the digital bandwidth. Okay, and that is equal to the number of bits per second that have to be saved or have to be encoded or decoded by the analog to digital and digital analog things. So that's the number of bits per second that we're talking about. Now, to get those, you would just multiply the sampling frequency by the number of bits per sample. So question number 1 says, if a signal is sampled at 1,000 times per second, okay, with 8-bit precision, what is the bit rate? The bit rate then is just the product of those two, because you have 1,000 hertz, which is samples per second, and you're timesing that by 8 bits per sample, which will give you 8,000. The samples will cancel out. Bits per second. Digital bandwidth. Okay, number 2, suppose you're in a band and you record your first time in stereo, which means you have 2 channels. Okay, the sampling frequency is 44.1 kilohertz. The kilo means a factor of 1,000, so that would be 44,100 hertz. Okay, and it was a 16 bits per sample. And then there were 2 channels. Okay, so for multi-channel bit rate, you have to take the number of channels times by the 1 channel bit rate. Okay, so that's the number of channels times the sampling frequency times the number of bits per sample. So that gives you yours. So in this case, the stereo bit rate is going to be 2 channels, okay, times 44,100 samples per second per channel, times 16 bits per sample. Okay. And you multiply 2 times 44,100 times 16, then you get 1,411,200 bits per second. Now we're just going to stick with bits for our class, lowercase, but in most computer things, when you see things like MB, GB, those are bytes, which are 8 bits. But for our class, we're just going to stick with bits. We're not going to worry about that factor rate. Okay, on the back, we have number 3. It says, what is different between 8-bit and 16-bit music files recorded with the same sampling frequency? Okay, so the 8-bit versus 16-bit. Okay, so, and sampling frequency is the same. So what that means is that if we're going from, say, here to here, okay, we want that to be the different kinds of levels that we can have. So they're thinking about this level, and this level is our softest and loudest sounds. Okay, then for the 8-bit, we get to have 256 steps going from there to there. Okay, but for the for the, so that's the, sorry, that's the 8-bit case. Right? But for the 16-bit case, you get to have 2 to the 16th steps, whereas 256 was 2 to the 8th steps. And that power means it's like 2 times 2 times 2, 8 times versus times 16 times. Which gives you which gives you 65,500 steps. So those would be like, oops, super teeny. I won't be able to draw them all, obviously, but you use your imagination. That's what we're talking about, right? Okay. So that's what we mean when we say the 16-bit signal has much finer amplitude resolution . 8-bit signal. Just more possible amplitudes that you can assign the different values of your wave. Right. In practice, it also does tend to impact the dynamic range a little bit, just because what is, below this, whether you have 8 zeros or if you have 16 zeros, the amount of things that get defined as those is greater when you have fewer. Okay. So the answer to that one is that the granularity of the amplitude resolution changes. Mm-hmm. So the granularity of the amplitude resolution depends on the bit resolution or number of bits per sample. So number 4 says what? Okay. Number 4 says what will increase if the higher sampling rate is chosen. Okay, so remember in what we did before, we have our wave. So we have our wave. Okay. Then the sampling frequency determines how often in time this is going to be sampled, right? Okay. So in this case, the sampling frequency would correspond to only these purple dots being encoded. Now, if you miss some of the ups and downs, you're not going to actually be able to reproduce this wave. So to recreate a certain frequency, or to recreate the wave or the signal, you will only be able to have frequencies that are sampled twice a period. Okay. So if you look at, I'll do an example here. If you look at from right here to right there, would be a period of this wave, and there's only one sample. So you actually cannot reproduce this. If you were to digitize it using this sampling rate dictated by the purple lines, you could not recreate this wave when you did the digital to analog conversion, okay? And so the way we say that is the highest usable frequency in the recording and the stored signal is half the sampling frequency or the sampling rate. All right, so as number 4 says, real quickly, so what this causes, so this undersampling causes aliasing, where things that were higher frequencies originally appear as lower frequencies in the recording. Okay, so number 4 says, what will increase if a higher sampling rate is chosen? Higher sampling rate. Okay, it increases the number of times per second. The value is saved. Okay. Which increases the file size because you just saved more points, right? Okay. So that's one. Yeah. One result is that it increases the file size. And the other one is that it increases the highest frequency captured in the recording. The recording captures this digitizing process. Okay, so that was number 4. Okay, moving on to number 5. Now we're talking about file size, right? So we want to know the amount of storage space. This is running enough. The amount of storage space is equal to the time that you want to store, but it has to be in seconds, times the bit rate, the number of samples per second. I'll leave you with the amount of storage space in bits. So number 5 says, how much information must be stored for a 1-minute recording? So time equals 1 minute. If the sampling rate is 10,000 samples per second, and each one is an 8-bit sample. Okay. So the storage space is equal to the time in seconds, 60 seconds, times the sampling frequency. Remember, this bit rate is the sampling frequency, and then the number of bits per sample, or the bit resolution. That's what we're talking about. So 60 seconds times 1000 hertz times 8 bits per sample. Remembering that hertz is samples per second. If you want to see how the units work out. And the seconds cancel out and the samples cancel out. We're just left with bits. So that's 60 times 1000 times 8, which is 4,800,000 bits, or 4.8 times 10 to the 6th, or megabits. Okay, that's number 5. Okay, so number 6 and 7 go together, just breaking it into 2 pieces. Okay, so number 6 says, what is the bit rate or digital bandwidth of a 16-bit stereo sample? So bit rate's the question mark. We have 16-bit. We have that word stereo in there, which implies 2 channels. And so a 16-bit stereo signal sampled at 32 kilohertz. That's our sampling frequency. So the bit rate is going to then be the number of channels times by the sampling frequency times by the number of samples, or bits per sample. Okay, so the bit rate then is equal to 2 channels times 32,000. Remember, you got to go to change it to hertz, which is samples per second per channel times 16 bits per sample. Okay, so the bit rate then is going to be equal to, when you multiply that all out, 1,240,000 bits per second. That's the bit rate. And then number 7 is just a continuation of that then says how much space is required to resave this 1 hour. So the time is 1 hour. But the trick with finding the space is that the time has to be in seconds. So you say, okay, well, in 1 hour, there are 60 minutes. And in 1 minute, there are 60 seconds. So then your minutes will cancel and your hours will cancel, and you'll be left with 3,600 seconds. Okay, so the space then is equal to the time times the bit rate, which was calculated in question 6. So we would have 3,600 seconds times 1,240,000 bits per second, which is 4.4 times 10 to the 9th, or gigabits, is the storage space. Okay. Sounds good. Okay, hopefully, let's see, there are a few more questions on here. Okay, machine processing to modulate your voice to sound like something else. Okay, so this kind of ties back into that idea of what makes speech sound like a certain person. Okay, so this is the bottom of the handout. If only fundamental frequency is raised, then it sounds like speaking at a higher pitch. It's the same person. So I'm speaking at higher pitch. Okay. If only the formant frequencies are raised, and it would sound like it's the same pitch as an original, but it sounds like a different person, right? With a shorter vocal tract. So, for example, a woman or a child, if you started with a man's voice. Okay, and then if both fundamental frequency and formants are raised, okay, that would be the processing you would do to convert from a male voice to female or child voice, depending. Because typically you would have both the higher fundamental frequency and the higher formants in females or children compared to male voices on average in general. Okay, hopefully those things are helpful. Hope you have a good day.